So far we've learned about 5 energy storage modes: gravitational, kinetic, thermal, elastic, and chemical. And we learned how to use pie charts to keep track of how energy is stored in a system. Then we went on to define what a system means, and then worked out system schemas that organized the interacting objects so that different things were in the system and different things were out. And we noticed how that changed our model of energy storage. Today we're going to find out that there are some situations where the pie chart model for energy storage would be better replaced by a different modeling device. This type of model is called the bar and system diagram. More formally, you should probably call it an energy bar chart and system diagram. As we get farther into this, hopefully you'll see why this new energy model works better for certain situations. And we'll also come up with a nickname for it that will make sense as we start to learn how to use it. Remember this event? We keep referring back to this in several videos now. The person is arming a spring-loaded dart gun. They release the spring that pushes a dart forward, and then the dart launches into the air. We modeled this with pies, and it worked really well. And part of the reason that it worked really well is because it was a closed system when we did this. So all the energy remained in the system. It was just changing the modes of energy storage. It went from all chemical to less chemical and some elastic, and then the elastic gave way to kinetic as the spring unwound and the dart started moving, and then the kinetic gave way to gravitational as the dart began to fly up into the air and gain elevation and then ultimately lose some speed. Pies work really well for closed systems. Pies work okay for some open systems as well. So when we had the dart, earth, and spring in the system and the person outside the system, our pie charts look like this. As the dart gun got armed, the spring got compressed, energy appeared that was outside the system before, and then that energy partially was transformed from elastic to kinetic, and then at the end, the kinetic and gravitational made up the pie. But once the total amount of energy transferred between 1 and 2, the size of the pies remained the same, and we were just looking at how do we divide it up between the different pie slices. Pies didn't work quite as good when only the spring was in the system. There was no energy at first because it was stored in the person, and then as the spring got armed, it crossed the boundary, and it was stored in the spring. And then as the spring unwound, energy was lost, so the pie shrunk in size, and then ultimately the pie disappeared. Now we saw a pie size that was changing here, and it worked out okay to use pies to model this. But the reason that it worked well, even though the pie was changing, is that all the energy was stored in the same energy storage mode. When we had the dart and the earth in the system, and the person and the spring outside the system, modeling this with pies shows a weakness of the pie chart model. At first there was no energy stored in the system because it was all stored in the person. Then it was all stored in the spring. Then the spring began to transfer energy to the dart, and so that energy that was stored as elastic energy in the spring became kinetic energy in the dart, but not all of it, and so the pie is kind of small. And then by the time we got to condition 4 at the end, then there was still some kinetic energy, but there was also some gravitational energy, and now all the energy had been transferred from the spring into the dart, and so the pie grew. So why do we need another model? Well, I think that last example showed one of the weaknesses of a pie chart. It's hard to interpret pies when the size and the slice proportion are both changing. It's hard for us to get an intuitive feel looking at pie charts of 2 different sizes that have different sized slices of the same amount of energy. Here's a way of explaining what I'm talking about. Imagine you had a pie that was 8 inches in diameter, and you sliced it into 8 slices, and you took 1 slice of that pie. That's a certain amount of pie. Now imagine you wanted the same amount of pie from a 9-inch in diameter pie. Obviously it would be a skinnier slice, but how much skinnier? Figuring that out would require some kind of fancy geometry formulas, and that's not something that you can just look at and get a quick visual interpretation in your brain. So it's hard to interpret pie size and slice size changes when they're both happening at the same time. That's a weakness of the pie model when the system is open. And another weakness is Because the pies are just snapshots in time, they track how the energy is stored at those instants, but it doesn't track how energy is transferred when the transfer goes across the system boundary. And that's something that we might want to know as we develop a better model. So we're going to switch to this new model called the energy bar graph and system diagram. Let's get a feel for how this works by going back to our wealth analogy that we began our study of energy with. So if we go back to the wealth analogy and remember what the guy's wealth system was like at the beginning, he had a large amount of money in savings, $30,000 I think it was. Checking was $5,000, $500 cash, and a $7,000 car made up his property. He made a change at first. And that change was he transferred some money from savings into checking, but he left his property and cash the same. So if we were to model this with a bar chart, the change is the savings goes down and the checking goes up by the same amount. Now let's look at the next thing that happened. He bought a car using money from his checking account by transferring it with Venmo. Here's the snapshots. The savings account and cash stayed the same. But after the transaction, his checking account went down and his property went up. If you measure the height of all the bars before and after, they would be the same. Let's represent his system by putting a circle in between these two snapshots. And that circle is going to be used to model what happened with wealth between him, his wealth system, and the rest of the economy. Well, one thing that happened was he transferred money out using a method called Venmo. And the other thing that happened was he transferred wealth in using a title transfer, which is another method of transferring wealth. Because the wealth that went out through Venmo matched the wealth that came in through the title transfer, the total wealth before and after is the same. The next situation was he sold his car to his sister. Let's take a look at how the snapshot changes. His sister gave him cash, so the cash bar goes up a little bit, and he lost the car, so the property bar goes down. Looking at the system circle, what were the wealth transfers? Well, wealth transferred out by a title transfer, and not as much wealth transferred in through cash. So if we added up the height of all the bars on the right-hand graph, they would be less than all the bars on the left-hand graph, because more went out of the system than came into the system. The last thing that happened in our analogy was he got paid, money was transferred into his checking account. So the before and after looks like this. Savings, cash, and property stay the same, but his checking account goes up by, I think it was $2,000. Looking at the system circle, how did that happen? Wealth got transferred in through an ACH, that's a method of wealth transfer, into his economic system. So that's the idea behind a bar and system diagram. The bar graphs show how much wealth is stored and what modes are used to store the wealth before and after. So those are snapshots in time. The circle in between shows what's going on in between the before and after in terms of wealth transfer in and out. We're going to just use the same idea tracking energy storage and transfer. So let's go back to energy and let's take a look at the scenario we've been dealing with the spring-loaded dart. In this first change, there's no energy stored in the system, but then after the change, there is energy stored in the system as elastic energy. Here's how we would model that. The before bar graph shows nothing. The after bar graph shows a bar of elastic energy of a certain height. Energy got transferred into the system in the meantime through something we call working. You can see I've abbreviated as a W. One of the three ways that we're going to see energy transferred into or out of a system is through this concept of working. Working is an energy transfer that involves a change in the state of motion of an object. So if something speeds up, slows down, starts moving, stops moving, those are changes in the state of motion. And when that is the change that we see, working was the way energy was transferred. Let's take a look at another situation. Here we have a hot coffee cup that cools off. Let's define the system as the coffee. Air is outside the system. At first, energy is stored as thermal energy. And that's the main energy storage mode. That's the only thing we're going to track here. After the coffee cools off, there is less energy stored as E-therm. In fact, I'm saying there's none. So energy transfer was out of the system, and it was through heating. So heating is an energy transfer that we can tell is happening when there's a change in temperature of an object. We abbreviate it Q, not H, for reasons that have to do with historical physics stuff. Let's look at another situation. Here's a before and after. It's a woman sitting out in the sun, and then afterwards she is warmer and also sunburned, it looks like. If we define the woman as the system, there's some energy stored as E-therm before, and after there's more energy stored as E-therm because she's warmed up by sitting in the sun. So energy got transferred across the system boundary into the system. This energy transfer mechanism is not the same as heating. It's related because there's a temperature change, but this is a temperature change without any contact. We call that radiation. So she is not in contact with the sun, either directly or indirectly, because the sun is 93 million miles away, but it still warms her up. So the sun is a great example of radiation energy transfer. Heat lamps are another example. Microwave ovens. The microwave oven would work even if there was no air inside, so it does not require contact, even directly or indirectly, and it happens just through radiation without contact. So there are three energy transfer mechanisms, three kinds of labels that can be on the arrows that go into or out of the system. W for working, that's when there's a change in the state of motion. Q for heating, that's when there's a temperature change and there's contact, which could be indirect contact. So in other words, if I'm touching something that's hot and I get warm because of that, that's also heating. And then radiation is when there's no contact, either directly or indirectly, between the hot object and the cold object, but yet there's a temperature change. So this gives you one more model to work with, and this is a model that's particularly well suited to open systems when we have energy transferring across the boundary. We're going to find ourselves using this quite a lot. It's a good setup for more complex energy modeling with numbers that you may learn about in a later class.